All right, section 8.2, connecting position, velocity, and acceleration of functions. You're going to notice that I'm going to kind of go through this section really quick because a lot of it is very repetitive. But hopefully you recall some of our discussion about the concept of particle motion from Unit 4. Okay, if you don't, please go back to Unit 4 and review it. But you have the derivative, right? So if you start with the position function, the derivative of that gives you velocity. The derivative of that gives you acceleration. Um, as long as t is, of course, greater than or equal to 0, because t is with respect to time when it comes to particle motion. So your teacher moves along a straight line at the front of this classroom. According to the values of the table, time is measured in seconds and x of t is measured in carpet squares. How far was your teacher's position from his starting position? So from t equals 0 to t equals 4. Well, at his starting position, he was at 2. When he ended, he was at 16. So he was 16 carpet squares away, right? What is the distance your teacher traveled? So total distance. Okay, what is the distance that your teacher traveled? Well, first, uh, he moved 2. He moved 2, right? And then minus 2 means that he moved backwards 2. Here, at this time, he didn't move anything. And then uh, from t equals 0 to t equals 4, right? And then here, between 2 and 16, between 2 and 18, he moved 16. So between this point and this point, he moved 4 steps. From this point to this point, he moved 2 more steps towards 0. From 0 to 2, from 2 to 3 seconds, he moved another 2 seconds. And from 3 to 4 seconds, he moved 16 carpet squares. So in total, he moved 24 carpet squares. So that's a review of displacement versus total distance, right? Now, example 1, particle motion with technology. You'll need your calculators out. And I'm not going to do the math in the calculator. I'll let you guys do that in the calculator. But part A tells us find all the values of t in the interval from 4 to 7 for which the speed of the particle is 5. All right. So basically, I need to figure out the speed. And if you guys remember that speed is equal to the absolute value of velocity. So we want to figure out when is speed equivalent to 5. Well, according to the problem, a particle moves along a horizontal line from 0 to 8. The velocity is given by the following function, and the position is given by s of t. It is known that an initial condition for the position function is 0, -3. Well, we have the velocity function, and all you got to do is take that velocity function, take the absolute value of it, and set it equal to 5. And you can see a graph. So the cascade abilities of the TI Inspire sometimes cannot effectively handle complex equations. It won't give you all of the values, right? If you use the numerical solve. So I think it's important that you, when you're given problems like this and you're using the calculator, to graph it and look for intersections. So take a minute and graph the absolute value of velocity and look for all intersections within the interval of 4 to 7. That is key, right? We don't care about all of the intersections, but graph v of t, graph y equals 5, and look for the intersections. One thing I will tell you is you should end up with two answers for this. T equals some second and another one. So take a second and figure that out. Next up, we want to write an expression involving an integral that gives the position function. So this is where this is important, okay? So we know that when t equals 0, the particle started at a position of -3. So we have to include that. Now, if you recall, right, when you solve for the position function, you're obviously going to be integrating the velocity function to solve for position. So when we do this, we have to take into account that the position is the integral from 0 to t, right? T always has to be greater than or equal to 0, from 0 to t of the velocity function, v of t. Well, before we plug in t, it's going to be v of x dx. But it is important to know that at this 0, this particle did not start at a position of 0. All right? So at the time of 0, this particle started at a position of -3. So we have to add that in, that the position was -3, and then we can use the integral equation to figure out the integral of velocity to figure out its position. So once we've set this up, the second part of this question says use that expression to find the position of the particle at time equals 3. Well, once you have the correct setup, you just got to do s of 3, and that's going to be -3 from 0 to 3 of v of x dx. Again, this is a calculator problem, so really you should just plug this in, remembering that v of x is just v of t. Okay, and once you solve this, you should get about -6.263. All right, find all the times in the interval which the particle changes directions. So remember that the particle changes directions when the sign of v of t changes. So you need to look at the graph of v of t, and when v of t changes signs, that's when we know, therefore, the object is changing directions. So again, graph v of t and look for when does v of t go from negative to positive. Basically, you're solving for the zeros of v of t. Is the speed of the particle increasing or decreasing at t equals 7? So how do we know that? Okay, how can we tell if the speed is increasing or decreasing when t equals 7? Well, we know that speed is the velocity basically, but of course to identify speed, we take the absolute value. But for this problem, you're going to figure out what is v of 7. What is happening at v of 7? What is the velocity? So it's -10 10.912. Okay, so this negative right here just tells us that the velocity is 10.912, whatever the units are per second, in the opposite direction. That's all that this negative tells us. So it doesn't really tell us if the particle at that moment is increasing or decreasing. But what we can do is figure out what is the acceleration at that point. And once we figure out the acceleration using our calculator, right, you derive velocity when t equals 7, and you get an answer of negative 10.561. So because both of these have the same sign, so because velocity and acceleration have the same sign, it tells us that the particle is increasing at t equals 7. And then you can also look at the graph of the speed from part A, and you can see that at at t equals 7, so if you go back to the original graph that you did, you can actually see that the curve is increasing at t equals 7, okay, for velocity. So if you graphed the absolute value for speed and then observe what's happening at t equals 7, you will see that at t equals 7, the curve is going up. So the points before it are less and the points after it are less. So the following table is fairly complete in describing expressions that are commonly seen in particle motion problems. You should kind of review these, right, for particle motion. And the reason that these are important is because it tells you what math to do when you see these types of problems, right? Like, for example, if they're asking you when is the particle at rest, that means that velocity is equal to 0. When is it moving to the right? It means that when is velocity greater than 0, right? The speed of the particle is the absolute value of velocity. Total distance traveled over the interval is going to be the integral of from A to B of the absolute value of velocity. Displacement is the integral of v of t without the absolute value. Position, remembering the initial position, and then from that, integrate, and so on. All right, so this is all of the ways that they can ask you about particle motion when it comes to integration or deriving. Okay. So let's review. You notice that these questions are very similar to what we did in Unit 4. The only added part is, adding the idea of integration. So the Space Shot is an amusement park ride that gently raises riders up a tower and then rapidly bounces them up and down using compressed air. The velocity of the Space Shot for time from 0 to 14 is modeled by the piecewise function, linear function as shown below, where t is measured in seconds and v in feet per second. So at part A is basically asking at what time in the interval, if any, does the space shot change directions? Well, I know that this is my velocity graph, and I know that the space shot is changing directions anytime velocity is changing signs, right? So before 6, velocity is positive. Between 6 and 8, it's negative. So when is it changing directions? Well, it's changing directions at t equals 6, at t equals 8, and then at t equals 10. Why and give a reason. Because velocity changes from negative to positive or vice versa at those points. At what time in the interval is the space shot between 0 and 14? Is the space shot the highest? So when it comes to this, the velocity is not going to tell you at what the velocity is not going to tell you where it is the highest, right? For the highest, we need the position graph. And we know that for the position graph, that means we need to integrate velocity. And the key points that we need to focus on are the endpoints. We got to use the candidates, right? So we're going to let y of t be the height and feet of the ride. And then we know that y prime of t is equal to v of t. And we're kind of asking when is that equal to 0? And we already solved it before, but we also have to use the endpoints. Okay? So our candidates are 0, 6, 8, 10, and 14 that we need to check. So when we're checking this, to figure out the position for t equals 0, 6, 8, 10, and 14, we know that we got to do the position function. Well, now we know that position function is going to be the integral of velocity. Graphically, we know that the integral of velocity from 0 to t, right, from the start to t, is the area under the curve. So the position function up to 0 is the integral of 0 to 0 of v of t. Well, that's just going to be 0. So that means the position at 0 is 0. 6, so from start to 6 seconds in, we got to figure out this area. So once you do that, you have a trapezoid, right? 1/2 of the height, which in this case is 20, times base 1 and base 2. You should end up with 100 as the position in feet. And you keep doing the same. So from 0 to 8 of velocity is going to be the area of this guy. And then what do you think we're doing with this area right here? Are we adding it or are we subtracting it? I hope you said subtraction. So we have the 100 from the previous example. We're going to subtract that triangle and you should end up with an answer of 40. All right, and then moving on from 0 to 10. Sorry for the space. I know that we don't have much. From 0 to 10, so now that we have up to 8 is 40, now we're just going to add that because it's above the x-axis. And that's another triangle of 40, which gives us a position of 80. And then the last one from 0 to 14, well, again, we have up to 10 is 80. And what do you think we're going to be doing with this area? We are going to subtract that triangle area, which is 1/2 4 times 40, and you end up with 0, which makes sense because it is a ride. So the position has to start and end at 0, right? So according to the table, the space shot is the highest at t equals 6. Okay, the ride is the highest at t equals 6 seconds with a height of 100 feet. All right, finding the total distance. So from that table that I just showed you, finding total distance, when you're finding just, you have to add up all of the parts, ignoring the fact that you went backwards, right? So even though this is a negative velocity, this means that you're going backwards, you're still moving a distance. So finding the total distance, review it in the table again if you need to, is equal to the integral from 0 to 14 of the absolute value of b of t. So what you have to do is all of these areas, right? We said this guy was 100, this one was negative 60, right? So this was negative 60 from the previous part in the problem. This one was positive 40, and this one was negative 80. Well, when you take the absolute value, you're going to say that the integral from 0 to 14 is 100 plus 60 plus 40 plus 80, and that gives us 280 feet. All right, write the expression for the ride's acceleration, velocity, and distance from the ground that are valid for the time interval from 10 to 12. Well, from 10 to 12. So I'm going to erase the marks I made here. We're going to focus on just the points from 10 to 12. Well, that's easy, right? Because this is just a line. So the velocity function from just 10 to 12 is just going to be the equation of the line, right? And the acceleration is basically the slope of said line. So I know right here that acceleration is a slope, and the slope of a line is a number. And in this case, it is negative 20, right? Rise over run. We've got negative 40, run 2. So negative 40 divided by 2. Now the velocity function is the line equation. And or we can do, well, yeah, let's do the line equation, because you can also just integrate this, because we do have the initial position, right, of this ride. We just don't have the position of it at 10, so we can't really use those points. So it is linear. Okay, so it is linear, and once you figure out the equation of that line, you should end up with negative 20t plus 200. And just to kind of remember, we usually use point slope form, so let's do that. So when you use point slope form, you got your y equals the slope, which we just solved for, t minus, let's pick one of these 2 points. I'm going to pick that point right there. So that's t minus 10, and then plus 0. So when you clean this up, you got negative 20t plus 200 as our velocity function. And then figuring out the distance from the ground that are valid for the time interval from 10 to 20? Well, I know that the position function is going to be wherever we are at t equals 10. So it's the position at 10 plus the integral from 10 to t. In this case, we should have put 12, right? But they want you to keep it in terms of t. So the t is going to be here. And then we got negative 20x plus 200 dx because it's the integral of the velocity function. All right, moving on. Quick MCQ practice with particle motion. Can you guys please use the QR code to figure out the answers? If you need help, you should be able to answer these without watching anything. Okay. So using the NUT strategy to interpret motion, motion integrals. Now, the reason that this is important is because you're always going to be asked, give a reason why. Okay, give a reason why. So the position of a particle moving on an x-axis in feet from the origin is given by x of t. The velocity is feet per second. Is given by v of t and acceleration by a of t. For each of the integral expressions given in the following table, interpret the meaning by filling in the missing parts. So you always need a noun, you need the units, and you need to explain the specific time that this is talking about. Well, in this case, you have, it's the integral of x prime of t, right? So, the integral of x prime of t, the integral of this derivative is just going to be x of t. So x prime of t is v of t, right? So this thing is like saying the integral of velocity. So this is the position of the particle. In feet, the unit is going to be in feet from the origin. And the time that we are focusing on is at t equals 4. And we know that it's at t equals 4 because of this part right here. So the question would say, find the position of the particle at t equals 4. This is what you would do. All right, so now that we've done all of these types of problems, okay, use the QR code to help you with this example if you need it, but try to figure it out. So we've talked about average value, right? But what if you're taking the average of the integral of speed? It's basically just the average speed. So it's the average of speed in feet per second. And in this case, we're going from 1 to 4. So from t equals 1 to t equals 4. So it's asking about what is the average speed for this particle from 1 to 4. All right, so finish up using those QR codes if you need it. You shouldn't need it. You should be able to fill these out, this table by yourself, and you should be able to answer these two multiple choice questions together. I do recommend that you make cards for this table. So if the expression said this, what is the mathematical translation on the back side? All right, good luck.